Imagine opening your eyes tomorrow morning, looking out the window and seeing a sky that is not blue but deep violet, or green, or completely black even though the sun is shining. It sounds like science fiction, but the color of the sky is not a fixed rule of the universe. It is the result of a very specific meeting between sunlight, air, tiny particles, and the way human eyes work. Change just one of those ingredients, and the sky changes with it. The strange part is that the air above us is almost invisible. You can wave your hand through it. You can look across a room and see the other side. So why should a nearly transparent atmosphere paint the whole world blue? The answer begins with sunlight. We often draw the sun as yellow, and from the ground it can look yellowish, especially when it is low in the sky. But sunlight is basically white to our eyes because it contains a mixture of many colors. Red, orange, yellow, green, blue, indigo, violet. The same colors you see in a rainbow are already hidden inside ordinary daylight. A prism makes this obvious. Shine white light into a prism and it spreads into a rainbow because different colors bend by different amounts. Nothing is being added. The prism is simply separating what was already there. A raindrop can do something similar, which is why rainbows appear when sunlight passes through countless tiny droplets in the air. But the atmosphere is not a prism. It does not neatly split the sky into colored stripes. Instead, the atmosphere scatters light. When sunlight enters Earth's atmosphere, it interacts with molecules of nitrogen, oxygen, and other gases. These molecules are much smaller than the wavelength of visible light, and that size difference is important. When light meets particles much smaller than its wavelength, a process called Rayleigh scattering becomes important. The rule is simple but powerful. Shorter wavelengths scatter much more strongly than longer wavelengths. Blue light has a shorter wavelength than red light, so blue light is scattered far more efficiently by the tiny molecules in the air. That is why the sky is blue. Not because the air is blue like paint, not because the ocean reflects upward, and not because space itself is blue. The sky looks blue because sunlight enters the atmosphere, and the blue part of that light gets scattered in all directions. When you look away from the sun, you are not seeing light coming directly from the sun. You are seeing sunlight that has bounced around through the atmosphere and been redirected toward your eyes. A huge amount of that redirected light is blue. This also explains one of the most important clues: space is black. Above the atmosphere, astronauts do not see a bright blue dome around them. They see the sun against darkness. Without enough air molecules to scatter sunlight across the sky, the space between bright objects remains black. The moon is a great example. The sun can be blazing over the lunar surface, but the sky above it still looks black because the moon has no thick atmosphere like Earth's. So the blue sky is really a sign that we are standing under a protective blanket of gas. But there is a problem. If shorter wavelengths scatter more strongly, violet light should scatter even more than blue. So why is the sky not violet? This is where the story becomes more interesting. First, the sun does not send exactly the same amount of every visible color to the ground. There is violet in sunlight, but not enough to dominate what we see. Second, the upper atmosphere absorbs some ultraviolet and violet light before it reaches us in large amounts. Third, human eyes are not equally sensitive to every color. Our eyes are very good at detecting blue and green, but much less sensitive to violet. When the scattered colors mix in our vision, the result we experience is blue, not purple. In other words, the color of the sky is not just physics happening outside us, it is also biology happening inside us. The sky we see is filtered through the atmosphere and then through the design of human eyes. On a perfectly clear day, the blue is usually strongest, high overhead. Near the horizon, the sky often looks paler, almost whitish. That is because light from near the horizon travels through more air before reaching your eyes. It gets scattered and rescattered many times. More colors mix together and the pure blue becomes washed out. Dust, moisture, pollution, and tiny aerosols can make this effect stronger. Clouds are another clue. If small air molecules scatter blue light more efficiently, why are clouds usually white? Because cloud droplets are much larger than individual gas molecules. They scatter many wavelengths of visible light more evenly. When red, green, and blue light are scattered together, our eyes see white. A thick cloud may look gray not because the water is gray, but because less light is making it through to the bottom of the cloud. Now think about sunset. At noon, sunlight reaches you by taking a relatively short path through the atmosphere. But when the sun is low near the horizon, its light must travel through a much thicker slice of air before it reaches your eyes. Along that long path, much of the blue and violet light gets scattered away in other directions. What is left traveling more directly toward you is richer in the longer wavelengths, yellow, orange, and red. That is why sunsets and sunrises can glow in warm colors. A red sunset is not the sun changing color. It is the atmosphere filtering the sunlight because of the long path the light has to take. The same sun that looked white or yellow at midday can look orange or red near the horizon because more of the shorter wavelengths have been removed from the direct beam. Sometimes sunsets become spectacular. After volcanic eruptions, wildfires, dust storms, or in polluted air, extra particles in the atmosphere can scatter and absorb light in more complex ways. That can deepen reds and oranges or create strange glowing skies. But there is a balance. Too many particles can also make the sky hazy and dull instead of dramatic. The most beautiful sunset is often not a dirty sky, but a sky with just the right combination of cloud, moisture, dust, and clean gaps for sunlight to pass through. The same principle explains something even stranger. During a lunar eclipse, the moon can turn red. Earth blocks direct sunlight from reaching the moon, but some sunlight passes through Earth's atmosphere and continues toward the lunar surface. Along the way, blue light is scattered away while red and orange light pass through more directly. The red glow on an eclipsed moon is basically the combined light of Earth's sunrises and sunsets projected onto the moon. Now the sky does not have to be blue everywhere. Change the atmosphere and you change the color. Mars is the famous example. Its atmosphere is much thinner than Earth's and is mostly carbon dioxide, with fine dust suspended in it. During the Martian day, that dust often gives the sky a rusty or orange-brown appearance, but near sunset, images from NASA rovers have shown a bluish glow around the sun. Fine Martian dust interacts with sunlight differently from Earth's air molecules, allowing blue light to stay closer to the direction of the sun while redder light spreads more widely through the dusty sky. So on Earth, daytime is blue and sunsets are often red. On Mars, the everyday sky can look reddish, while the area near the setting sun can turn blue. Same sunlight, different atmosphere, different sky. This matters because sky color is not just a pretty detail, it tells scientists what an atmosphere is made of. The color of light scattered by an atmosphere can reveal the size of particles, the gases present, the amount of dust, and even whether clouds or hazes exist. When astronomers study planets around other stars, they look for tiny changes in starlight passing through those planets' atmospheres. The idea is similar. Light carries clues about what it has traveled through. Even here on Earth, the sky is giving us information all the time. A deep blue sky often means the air is relatively clear and dry. A pale, milky sky may mean there is haze, humidity, or tiny particles suspended in the atmosphere. A red sunrise can signal dust or moisture in the direction of the sun. The sky is not just a background, it is a giant changing display of atmospheric physics. And yet most of the time we barely notice it. Every clear day, a star shines on a planet wrapped in gas. That starlight contains a rainbow. The smallest molecules in the air scatter the shorter waves more strongly. Our eyes gather the scattered light and turn it into the color we call blue. Then at sunset, the same atmosphere stretches the sun's path, filters the light differently, and paints the horizon orange and red. The sky is ordinary only because we see it so often. But the moment you understand what is happening, it becomes almost impossible to look at it the same way again. The blue above your head is not just a color, it is sunlight, scattered by an ocean of air, revealing that we live inside a thin, fragile atmosphere between the ground beneath us and the darkness of space.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!